А есть ли звук? Раз, раз. Ага, хорошо. Так. Okay, so we continue tensor products. So last time we considered the following situation. We have two modules. Then we define the tensor product of modules. And what is the simplest possible element in this tensor product? Well, this is the simple tensor. We have element like this. So this is simple tensor. Of course, here we assume that element m is in the module m, element n is in the module n. And any tensor, so any, say you take t for tensor in this tensor product, then we can write this t, of course not in a unique way, but at least we can do this as a finite sum of several simple tensors. This follows from the definition. If you go back to the definition, we define this tensor product as a quotient, and all elements in this, not in the quotient, but in the module T that we defined last time, for finite sums. So this little observation is very useful from a theoretical point of view and from a practical point of view. For example, you can give the following definition. Suppose you have now several modules and a couple of maps. So let F be a map, say from M1 to M2, and also have G, which is a map of modules N1 and N2. So let F and G be map of modules. So then we can define tensor product of the maps. So F tensor G. This will be a map from the M1 tensor product with N1 to the M2 tensor product with M2. And how we can define this? Well, if I want to define something, I can define this on simple tensors, right? And then just extend by additivity to all possible tensors. So on simple tensors, the definition is quite straightforward. So map of modules. So then the map defined by, so if I apply F tensor G, this is a map, and I want to compute this on a simple tensor in M1 tensor N1. So this will be something like M tensor N. Well, not surprisingly, you just do this kind of component-wise. You say that this is F that you compute on M. This will be an element in M2, and then take tensor product with G and compute it on N. And this, of course, is an element in the M2 tensor N2. So defined by this formula on simple tensors, and extended by linearity to all tensors. Right, so if you have a finite sum such elements, you know how to compute this on finite sums. You just apply this component-wise to each element in the sum. So this is the tensor product of your modules, and there is a simple observation. So I would say, not an exercise, but I would say clearly, you have the following. For example, you take F1 tensor G1, and you want to understand the composition with F2 tensor G2. If you just use the definition, you'll get that this is F1 composed with F2, tensor product with G1 composition with G2. Immediately follows from the definition. Okay. Now let's discuss some very basic properties of the tensor product. So there are several propositions, and the first proposition is the following commutativity property of the tensor product. So suppose M and N are R modules. So then you can say that the tensor product of the N and M, of course over the ring, is the same thing as the tensor product of M and N. So in other words, this tensor product of ring is a commutative operation on modules. Well, the proof is quite straightforward. Again, we're going to use simple tensors. So first of all, we can observe that there is a map phi from the Cartesian product of two modules, so M and N. Now, I want to switch these factors, so this is from M times N to the NM, tensor product of NM. And this is defined by the following formula. So if you want to compute this on the pair M and N, well, you just say by definition that this is the tensor product of the N and M. So this map is bilinear. And since this map is bilinear, it induces a map on the tensor product. So it induces map F from the tensor product of the M tensor N, the N tensor M. So in other words, on simple tensors, you just switch the order of two factors. So F on the simple tensor M tensor M is equal to the M tensor M. Okay, but you can do, of course, the same thing in the other direction. So this is for simple tensors, and again, this is extended by the linearity to all tensors. And of course, I have map in the other direction from the M tensor M to the M tensor N. And if you look at the compositions, well, this will just, on simple tensors, that will be switching two times, and so it will be the identity in both directions. And if this is identity on simple tensor, this is identity on any tensor. So that's quite elementary proof, I would say. But the notion of simple tensor is quite important in the proof. Okay. So there are a couple of other properties which are equally easy to show. Maybe the next property is the following. M is an R module. So then the tensor product with the ring, maybe I'll put the ring first, it's actually isomorphic to the module itself. So tensor product with the ring doesn't do anything. And of course the proof is very easy. Again, you start with the simple tensor, so something called the form R tensor M, and you define the map. So there is a map that sends this simple tensor to the element in the module Rm. Okay, so this makes sense. R is an element in the ring, so that we can define the product. And you can go in that direction. So this will be a map F from the tensor product of R over R with M to the M. And you can define map G in the other direction. So G, this will be a map from M to the tensor product of the R and M. And G just takes element M and sends this element to the one tensor M. And again, you can check immediately that the composition of the f and g is the identity, and the composition of the g and f is the identity. Maybe just a little comment in one direction. So suppose I first apply f. So let's look at the composition of the g and f. So f starts on the simple tensor, r tensor m. So this will be, if you apply f and then apply g, this will be 1 tensor rm, right? Just by the definition of f and g. But now you know that in the tensor product you can switch around this r. So as a tensor, this is exactly the same tensor as r tensor m. And the composition in the other direction is also easy. Okay. Okay, so next proposition. Let m, n, and l be R modules. So then we have the so-called associativity of the tensor product. You can form tensor product of these three modules, and it doesn't matter what tensor product you compute first. So there is an isomorphism like this. And the proof is very similar to the proof of the first proposition. It's a little bit longer, the maps. Well, maybe not really. Okay, but anyway, so I want to leave this as an exercise. Elementary property. Okay, and now I want to discuss how tensor products are related with sums and products. Okay, for the sums we have the following straightforward property, so proposition. Now I suppose that M is an R module, and we also have a family of modules, so say an S parameterized by some set S is an R module, and this thing is a family of R modules. So in other words, just a set of R modules, and this set is exactly the set S. So then we have the following property, that if you take the tensor product of the M with this potentially infinite direct sum, then this is isomorphic to the direct sum of tensor products. Okay. Unfortunately, this thing is too wet, so if you don't have questions about this, I'm going to erase this right now, so it won't be so wet when I'm going to write on this. Okay, so the proof has the same idea. We need to define maps f and g in one direction, the other direction, and then we will see that the composition of these two maps is identities. Okay, so in one direction, the map is straightforward. So if you start with the tensor product of the module M and this direct sum, and want to get element in the direct sum of tensor products, Well, how you can do this? Well, what's an element here, a simple tensor? Well, a simple tensor looks like this. You have some element m, and then you have tensor product with what we call this infinite vector with as many components as we have elements in the S. So let me write this as ns. And we need to send this again to the infinite vector of simple tensors. This will be this infinite vector. Very straightforward definition. In fact, it's probably the only thing you can come up with when you look at these two modules. Now, let's do the map in the other direction. So in the other direction, I'm going to define in two steps. First of all, I'm going to define maps GS. This will be a map from the M tensor NS to the M tensor direct sum of all these NS. So this is simply defined, well, you take again a simple tensor here, M tensor NS, where of course little ns is supposed to belong to the capital NS, and you send this element to the following. You take the tensor product of M and then use the canonical embedding when we discuss the products and sums. We define these canonical projections and canonical injections. So this is the canonical injection U at S. So this is the definition of the map in GS, and then we can define the map G that goes in the other direction. So this is from the sum over S, M tensor product MS, to the M tensor product with this sum. And so here an element has the following structure. So this is some ms depending on the index s, tensor ns. So infinite vector of the following form, and you send this to the following thing. You take the sum, which will be of course a finite sum, so sum over s, and then you apply gs to the ms tensor ns. So this is how you define maps, and I leave this as a little exercise to check that if you take the compositions, you will get identities. So maybe a remark here that of course this map F can also be used not for just direct sums, but also for products. So we have the map F with exactly the same formula. Okay, but this is unfortunately is not an isomorphism in general, but we have the following properties. So first, F is surjective if M is finite, and the second property that F is bijective if M is if M is finitely present. So I'm not going to prove this right now, we'll do this on the seminar, but I think it's important to know that this works in a straightforward way for direct sums, but for direct products you need some additional assumptions assumption that M is finite give you a surjective map, and assumption that this is M is finitely presented give you a bijective map, and also a good exercise to find counterexamples. So, for example, take M which is not finite, right, and try to construct a map which is not surjective and also not injective. Or maybe another exercise would be take M which is a finite, right, so then you have a surjective map, but this M is not finitely presented, so this map won't be injective. So this all the things that we can do. Maybe some of them we will do in the seminar. Okay, and we go to the next section. Just quite a short section. I just want to mention this, it might be important later. So the extension and restriction of scalars. So we have the following situation. We have phi, a map of two rings, R and S. So then the definition of the extension and restriction of scalars is the following. I can start with the module, say, so that M be an S module. So then I'm going to use the following notation. Phi with the lowest star of M is the module M, as R module. So in other words, we can just use this homomorphism of rings, and if you have any module M on the S, you can consider this as a module over R. Alright, so to understand that this is an R module, what you need to know? You need to know how to multiply an element from the ring R on the element M in the module, right? But you can do this by applying phi. You apply phi to the R, this should be an element S, and you know how to multiply element in S and element in the module. Yeah, that's if you want to come precise language, that's a functor from the category of S modules to the category of R modules.
It is the same set?
Yeah, it is even as a abelian group, it is the same abelian group, but it is defined over a different ring. And the definition of the ring structure is given by this formula. And this is called the restriction of scalars. So the separation phi lowest R is the restriction of scalars. So this is the first part of the definition. Now I want to define the extension of scalars. Okay. Well, in many examples, R is just a subring. So if R is a subring, it's quite natural to call this restriction of scalars. I'm just going to finish the definition and we doing an example that you've probably seen already in the algebra course, or maybe in the geometry course, I'm not sure. But this will be the well-known complexification and realification of vector spaces. Okay, so now I want to define the extension of scalars. So here I do the following. I start with the module N, which is a module over R. And the extension of scalars will be an operation that will give me a module over S. So let N be an R module. So then phi upper star of the N. This is by definition, I take this module N and then take the tensor product with S. and phi upper star of n is an S module, and this is called the extension of scalars. Because maybe I need to, again, like in the previous part of the definition, in parentheses, add how I understand this as an S module, or an element here, in general, yeah, this will be a finite sum of Si tensor Ni, right? This is an element in the phi upper star of the n. Yeah, and now I want to understand why this is an S module, so I want to understand how I can multiply this on any element in the S. So what would be a product like this? So how to define this operation? Well, in a very naive sense, this will be again the finite sum S, Si, tensor Ni. No, we use phi because we want to think about S as a module. Over R. And this map gives us exactly, well, this gives us a little bit more, but this at least gives us the structure of S as an R module. So notice here that S is an R module. And the explanation is exactly the same line, essentially, right? Because, well, I can as well think if I understand S as an R module, then I take well, no, if I just take that's the product of two modules, it will be automatically an R module. I need this to be an S module, so I still need this. But if I want to understand why S is an R module, well, what's the action on the ring R on the S? Well, you just apply phi to the R and take a product with S. So any
star to S, yeah? It's like we apply F star the subindex to S. It's an S module.
Yeah, sure. So I just want to say it's important to understand that any map of the rings give the structure of this second ring, the structure of an R module of the first ring. In this tautological sense by this formula. Okay, so I want to propose you an example. As you know, probably. So this is the following example. The map of rings is just the embedding of real numbers into the complex numbers. And then you have two operations. So phi lower star is doing the following thing. So you start with a complex vector space, and you consider this as a real vector space. So this is V as real vector space. So the realification of the complex vector space. For example, you can notice the following. If the dimension over complex numbers of the vector space C is n, so then the dimension over real numbers of the phi lower star of the V, of the V is what? Well, take the simplest possible example. What if V is just a copy of C? If you consider C as a real vector space, this is a two-dimensional thing. And if you have finitely many copies, well, you just kind of apply this to each copy. Or in other words, you can say the following. If you have a basis in the V, say E1 up to En, so what would be the basis here? So the basis will be, so say this is the basis, then the basis here will be Ei, and then also this thing. So this will be the basis. Okay, so this is, you consider the complex vector space as a real vector space, and what will be the extension of scalars of the phi upper star of the now real vector space? Maybe I call this W. And this will be just the tensor product over real numbers with complex numbers. So this is the complexification of the real vector space. And let's do the same observation. So suppose the dimension of real numbers of the vector space W is equal to n. What's the dimension of the extensional scalars of the W over complex numbers?
Well, it should be like n over 2 in case n is divisible with 2. So
Again, try the simplest possible case. What is W is R? What this separation is doing?
It should be just 2n, no?
No.
If W is R, then it will be tensor product of C and R over R.
Mhm.
This is just this C as an R module, no?
Remember that we don't consider this extension scalars as an R module. Right? This is what I mentioned here. Of course, you automatically have, because S is an R module, this is an R module, but I want to consider this as an S module. So, in the simplest possible example, when W is just real numbers, then pi upper star over W, this will be the tensor product of the C over R with R. But, yeah, so this is equivalent isomorphic to the C, right? This is what's one of the properties that we proved in the beginning. If you kind of multiply on the ring over the same ring, you can cancel this part. But you want to consider this as a C vector space. So it's one dimensional. Yes. So this is n.
answer the question, but they are isomorphic as R modules, as C modules. Are these two isomorphic as C modules?
Of course, they are isomorphic as C modules. Well, well, this is one dimensional over C, and this is one dimensional over C, and the dimension is completely invariant for vector spaces. And if you want to do this again using a basis, you can write something like this. So the W has a basis of this form. Now I use this notation to write this R, that this vectors span V in the unique, well, as a basis over R. So then you can say that the complexification is spanned by the same vectors. So you can consider the same linear combinations, but now coefficients that you can use, not just real numbers, but complex numbers. This is one more explanation why this is. If the dimension is n, it stays n, but over a different field. Of course, it is not related to the real numbers and complex numbers. If you have any extension of the fields, you do the same operation. And if you have any map, more general, any map of the rings, you still can do this operation, the extension and the restriction of scalars. Now maybe let me mention a couple of properties of the extension of scalars and restriction of scalars. So proposition. So as before, I want to assume that phi is the ring map. So what we see in these examples with the extensional and restrictional scalars over real and complex numbers, that if you start with the finite dimensional vector space, you do the operation, you still get the finite dimensional vector space. So this is in fact true in general, and this is what this proposition is about. It has two parts, for the extension and the restrictional scalars. So in the first part, we have the following. If M is a finite R module, then you do the extension of scalars, and you still get the finite module. So the extension of scalars is finite, but of course in this case as an S module. Finite S module. The second part is about the restriction of scalars, and you need to assume a little bit more. So if S over R is finite as module, and we can consider S as a module over R, and we want to assume that S is a finite as module. So then, if now N is a finite S module, so then the restriction of scalars is finite. Is finite. It's a little bit surprising at all. Maybe there is something wrong with this proposition, so let's check. Maybe I need to correct something in the statement. Let's do the proof, and then we derive the correct statement from the proof. So, well, maybe let's start with the extension, first with the extension of scalars. So the extension of scalars maybe I need to write this on the one. It doesn't matter on which side I write this S, the tensor product is commutative, but it may be more convenient to write this on the left because we assume that we act using the ring from the left, not from the right. Okay, so if I assume that M is spanned by some elements, so generated by some elements over the ring R, yeah, so probably I need this additional assumption about the fact that S over R is finitely generated in this situation, because I assume that S is also generated by finitely many elements over R. So then I can see that this extension of scalars can be spanned using SI tensor MJ, again over R, and of course I is between 1 and K, and L is between and J is between 1 and L. Yeah, so I need this additional assumption that S is finite over R for the extension of scalars. No. For example, you start with an R module and take this tensor product.
So we just should be replace lower star and upper star, I guess.
Yeah, I just want to correct. So if M is infinite, then this is finite S module if S over R is finite. So this will be the first part. Now the second part is this: if N is a finite S module, then phi lower star of N is finite. Yeah, and the proof of the second part is more or less automatic, because if you assume that N is a finite module over S, so you can span this by N1 Nk over S. Now we want to consider this as an R module. Well, as an R module, so phi lower star of N, this is still spanned by the same elements. But you only need to consider this not over S, but over R. Yeah, I think about this, and it looks like in the beginning everything was correct. Because exactly in this situation, right? So if you know this, right? So then if you try to write an element, okay, so if n is finitely generated over S, right? Wait. Present is finite as module. Yeah, so okay, so suppose this n is a finite S module, so then what I can do is, and I want to consider this as in the second situation, I do the restriction of scalars, so I want to consider this as an R module, right, as an R module. Yeah, so let's look at this thing as an R module. So this is phi lower star of n. And if I take any element here, right, so what would be a general form of an element here? This will be a finite sum with coefficients, say, Si and I, right? So I is running between 1 and some, say, k, right? So any element here, well, this is just n, right? And I want to consider this as an R module, so, but still any element here is this finite sum, because this is a set of generators. Now, if I can present, if I take this Si, and I can present this as a finite combination with R coefficients, right? So if I take any Si and can present this as a sum, say, with the matrix Si, say J, and I have some generators. Maybe I already used Si, so maybe let's call the generators something like Tj. Right, so this Tj are in the S, and the matrix elements are in the R. Right? If I can write like this, so then this will be a finite sum. Of course, the summation over J is finite. So then I can present every element. So I can present every element as a sum is S, J, I, T, J, N, I. Right? But now the coefficients that we have here are elements of the ring.
So now n generators of n is S, I, J, and I?
No, n are generators of the n over S.
Yeah, like this, but over R.
Oh, and yeah, because the coefficients now, these coefficients are over R, the generators of the phi lower star. So if you look on the phi lower star of n, and you want to understand the generators over R, you need to take all such products.
So why it's still K generators?
No, there's not K generators.
So like there we have.
This is a product of K and L generators.
Yeah, I understand. So there we have the example of R and C.
Mm-hmm.
And there was the dimension was n and m after.
No, this is the restriction. This is restriction of scalars. So if you start with k-dimensional vector space, because C over R is two-dimensional, you'll get to n. So here, actually, this is generated by the L elements. So this will be k times L. Yeah. So in the beginning, everything was correct. So for the second part, I need this additional assumption.
And why we don't need this? First part.
just let me check if S over R is finite as module. Now the second part, it looks correct, and the first part is correct. So now let's go to the first part and correct the first part of the proof. Well, I know that M is finitely generated, right, in this case as an R module, and now if I just look at the tensor product of the, so this tensor product, so then I can just say that phi upper star over M is spanned over S by the same elements. So this is the observation. Well, how we can notice this? Again, you need to take some element in this phi upper star of M, because this is tensor product, and any element here is a finite sum. This is a finite sum, say of the elements Si tensor Mi. But again, if I have some of simple tensors, I can always assume that the second element is just the generator, because otherwise I just decompose this into the sum of generators and can rewrite any sum of simple tensors in this way. So any tensor here looks like this. But this is exactly how we defined, maybe to be completely precise, if I want to write not just these things, I want to write one tensor M1, one tensor Mk as the generators, because this is exactly the sum Si, one tensor Mi, and this is how Si is multiplied on an element in the phi upper star. So here we don't need any additional assumptions. So extension of scalars, the tensor product preserves the property being finite without any assumptions. And here you can see that we need actually this additional assumption because of this expansion. Now, of course, I think it won't be hard to find a counterexample for the second part, where if you drop the assumption that S over R is finite, and if you take, I think the counterexample would be something like this. For example, if you take Q inside the real numbers, this is not a finite module, of course, so this is not true. S over R is not finite as a module, and you want to take a finite S module, well, take again R. So R is not finite over Q. So this assumption is essential, but there is easy counterexamples. Okay. So just a general observation of the extension and restriction of scalars. Now there is one more general property about the extension and restriction of scalars. So this is the next proposition. So as before, phi is a ring map. So the map that I'm going to call again iota, because this is an embedding, so from the module n to the extension of scalars applied to the restriction of scalars of n. And this map is defined as follows. You take an element n and you just send this element to the tensor product of 1 and n. So this restriction of scalars and then extension of scalars is the following. You can write this also as S, tensor product of S over R with n. Right? You start, maybe this is R module. You start with an R module. You consider this R module as, sorry. Yeah, you start with an S module. You start with an S module, you consider this as an R module, and then you again multiply this over R with S. Kind of do this composition. So you have the canonical embedding of the n back to the composition of these two operations, and the embedding is given by this formula, 1 tensor n. So, so then this map iota is injective, and the image of iota is a direct summand in this module, phi upper star, phi lower star of n. Well, meaning that this module is a direct sum of the n and something else. So this will be n plus some maybe complementary module C. So this is what means that n is a direct sum of this module. Okay, so let's consider the short exact sequence where you start. Well, we don't know at the moment this is short exact sequence, but at least we have a map iota to this phi upper star, phi lower star of n. And then we just take the canonical surjection to the quotient. Well, we have a map like this. So this is the map. So I claim that this module, this is an S module, it can be presented as a direct sum of two modules. One of the modules is n, and there is also some other module which I call C here. So C, because this is complementary module. Okay. And in fact, it would be enough to show that this short exact sequence splits, because if I can construct a retraction here, which I'm going to call rho. So, and this rho is given by the following formula: S tensor n is equal to the product Sn. Very straightforward definition. It's not easy to, not hard to see that this is actually just a map of S modules. Okay. So I then use this definition of the iota, which is given by some explicit formula, definition of the rho, which is again given by explicit formula, to check that if you take the composition of the rho and iota, you get the identity map on the n. So I'm going to erase, and you can use this pause to check that this is actually true. And from this formula, everything follows, because if you apply this identity to some x, and you get that iota of x is equal to 0, then from this identity x is equal to 0, so iota is injective indeed. So we have a short exact sequence, and we have a retraction for the first map, so we know that such short exact sequence splits. Well, when I just beginning to write the short exact sequence, I didn't know that this is an embedding. So, well, we need to check this somehow, right?
Yeah, but there we say that this is injective.
Yeah, I'm just saying that you can explicitly define a map rho that goes in the other direction, and this rho is inverse on the left. And whenever you have such a situation, you have inverse on the left, the map you consider is injective map. So yeah, if you know that there is rho, then you know this is injective. And if this is injective, this is automatically short exact sequence because it's just defined. You take an embedding and then you just complete this to short exact sequence by adding map to the quotient. So this is short exact sequence, and this short exact sequence splits. So that's the end of the proof. Okay. Okay. Next section, flat modules. So first I start with the exactness property of the tensor product. Remember when we defined the home, we saw that they have a couple of exactness properties, right? So so-called the exactness of the home on the left. Now the tensor product has the property of being exact on the right. And this means the following thing. So for any short exact sequence, well, it's not really exact sequence, for any exact sequence which is exact only on the right, so m prime, alpha, m, beta, m double prime, 0. So the sequence, when you just take this sequence and multiply everything on the n, so m prime tensor n, we have a map here which is the alpha tensor product with the identity on n. The same for the second map. So for any exact sequence like this, the sequence obtained by tensoring with the module n is exact. So this is the exactness property of the tensor product. So in other words, if you have a surjective map, well, this will be part of the information, but tensor product of surjective map and the identity is still surjective. And from this, if you want, you can derive the tensor product of two surjective maps is surjective. But anyway, so let's check that this is true. Okay, so I'm going to start with this second diagram. So there is a map here which is alpha tensor product of the identity on n to the nth. So I just take part of this diagram. So first two modules and this map between these two modules. And then I complete this to a short exact sequence. So in other words, C is just the co-kernel of this map. So where C is the co-kernel of the alpha tensor product with the identity map. So I know that this sequence is exact by construction. So my goal is to show that this sequence is actually isomorphic to this sequence. So that's the plan of the proof. Okay, so maybe it will be convenient to write them together. So I have this sequence. And I also have something that I need to show. Okay, so I start with the map F. So the map F is a map from the C to the tensor product of the m prime tensor n. Well, maybe I also want to give a name to this map to the C, so let's call this map pi. Okay, and here I have alpha tensor the identity on n, and this is beta tensor the identity on n. Well, we know that when I consider the composition of these two maps, so take the composition, so there is map F, such that if I apply pi, then I apply F, I'll get the composition of the beta tensor product with the identity of n. So, yeah, how we can show that there is a map like this? Well, I look at these two maps. So the composition of these two maps is 0. Well, how you compose two tensor product of maps? This will be the composition of the beta in alpha times the identity, and this is 0 because given well, this is exactly this term, so the image of alpha is exactly the kernel of beta. So this composition is 0, so this is 0, right? And now, if you have a map. Well, you consider this map beta tensor product with the identity. This is a map defined on this module, M tensor n, and in fact it is 0 on the image of the map alpha tensor the identity. So it is a map actually defined on the quotient, so on the C. Right? So if you wish, you can think about this, how you can define F on the, well, so you want to understand F on the class, say on the simple tensor, right? So any element in the C is such a class. You can say, well, by definition, that what you do, you just apply the map beta times the identity on n to a representative of this class M tensor n. And this doesn't depend on the representative, well, because the difference between two representatives is exactly in the image of the alpha times the identity on the n. So this map F is well defined. And it's a usual observation. If you have any map defined on a module which is 0 on some submodule, then actually this map is defined on the quotient. So this is what I use to define map F. Okay, so I constructed the map F which goes in one direction from C to this tensor product, and also there is a map G going in the other direction. So let me take some M double prime tensor n, that's the simple tensor in this tensor product. I want to define map G on this simple tensor. So first of all, I know by the exactness of this diagram that an M double prime is beta of some M. Well, because the classes are kind of representative plus the image of this map.
Yeah.
But if you apply this map, beta.
We know that image lies in kernel.
Yes.
So that's why we don't broke anything. Or is
Well, maybe I use the general remark is the following: you embed M prime into M, right, and then have a quotient. Now, suppose you have a map, say, capital F to some other module n, and you know that this F restricted to the M prime is 0. This is exactly our situation. So this is the map, and restricted to this submodule, it is 0 by this. Now, in fact, this F is a map on the quotient. So how you define this, or if you want to understand F on the M on some class, so now let me write the class as some representative plus M prime, right? You just say by definition that this is capital F computed on the representative M. Now if you have two different representatives, the difference between these two different representatives will be in the M prime. Yeah, so this is how you can use this general observation all the time. Now I want to define map G going in the other direction. So I take any simple tensor in the M double prime tensor n. Because of the exactness of the given diagram, I know that any M double prime is necessarily of the form beta of some M. And this allows me to define the map G. So I'm saying that g on this simple tensor is by definition pi applied to the m tensor n. Right? So m tensor n is a tensor here, so I can apply pi and get some element in the C. Now, of course, there is a question why this map is well defined. So G is well defined. Well, what's the problem? The problem is for this m double prime, I can choose different m's that satisfy this condition. So, but if I say that m double prime is the beta of m1 and also beta of m2, well, at least I know that if I apply beta to the difference, I'll get 0, right? Now, if beta of some element is 0, this is alpha of something. So m1 minus m2 is alpha, say, of some m prime. Okay? So there is this element m prime.
So P composition is alpha out of the prime is just 0 because this is short exact sequence on the.
Yes. So now, if you apply pi to the m1 tensor n minus m2 tensor n, right? You want to see that answer doesn't depend on this representative, so this has to be 0, right? But this is pi applied to the m1 minus m2 tensor n, right? And this is alpha, this is pi applied to the alpha of the m prime tensor n, or I can say that this is pi applied to the tensor product of the alpha times the identity. So this is composition of the pi alpha times the identity of n, and this is all applied to the element m prime tensor n, which is 0 by the definition of the map pi. So we have a well-defined map. So we have a well-defined map. So what we need to check is that the compositions in both directions, now this is not as straightforward as in the previous propositions. So I'm going to do the computation. So I'm going to compute the composition of the f and g, and I want to see this as the identity. So this composition on any simple tensor m double prime tensor n, well, I choose the representative as before to define map g. I choose any m satisfying this property. So then I can write that this is the composition of the f. Composition is pi, and this is applied to the simple tensor m tensor n. Now, by construction of the f, I know that I have this. So I can replace this composition of the f and pi by the product, tensor product of the beta, tensor product with the identity on n. Okay, now what I see? Well, I see that this will be beta applied to m, tensor product with n. But beta applied to m is exactly m double prime. So this composition of the f and g is the identity on any simple tensor and hence on any tensor. Now let's do the composition in the other order. So composition of the g and f, say on the class of a simple tensor m and n. Okay, so the class is again, I can think about this class as the pi applied to a simple tensor m and n. That's exactly the same thing as the class. Now, composition of the pi and f can be replaced by the tensor product of the beta and the identity on n. So this is g composed with f composed with pi applied to a simple tensor m tensor n. Now this composition is the same thing as the beta and the identity on n. So this is g composition with the beta as the identity on n applied to the simple tensor mn. So this will be g that I need to apply to the beta of m times n. Okay. Yes, now the last step is just to remember the definition of the map G. When I define map G, I was saying that this is pi applied to the pre-image of the first factor times the second factor. So here in this case, it's kind of given as beta of something. So the pre-image is given as m. So if I want to apply G to this, all I need to do is to say that I'm applying pi to the simple tensor m tensor n by definition of the map G. And this is the same thing as the class. So again, this composition on any class gives me the same class. So the composition in this order is also the identity. So what we can see is that I have a short exact sequence. I have another sequence which I don't know which is exact or not, but I have a maps which give me an isomorphism of these two sequences. So this is exact, this is also exact. Here. Yeah, so I wanted to define map G, right, from this tensor product to C. So simple tensor in this tensor product is m double prime, so this is double prime, times tensor n. So I want to define G. So I know that any such m double prime is of the form beta of m. Right? This is the exactness of the given short exact sequence. Or not short exact, well, this exact sequence, which is exact on the right. So I define G by this formula. Right? I choose the pre-image m, and I use this to give a formula for the G. So in other words, I can also say this is the same thing as the class of m tensor n. Right? So I take a simple tensor here, so the form of this form, it is, then I can find tensor here or here, and then I apply pi to this tensor and get an element in the C. So this is how G is defined. Now there is of course a problem because I choose the representative m that satisfies this equation. So what if I choose two representatives, m1 and m2? So I'm doing this. M double prime is beta of m1 and m2. And then, because the beta on these two elements are the same, so beta applied to the difference is 0. But if beta applied to some element is 0, again by looking at this exact sequence and this term, beta of something is 0, it means that this something is in the image of alpha. So I can write this m1 minus m2 as alpha of some m prime. And now I just do the computation. I want to see that if I choose two different representatives, this answer, this pi of a simple tensor, is the same, or classes are the same. And this is a simple computation, so I apply pi to two such simple tensors, right? So then I know that for tensor product, this is the same thing as the m1 minus m2 tensor n, so the tensor product is distributive. So then I just plug in that m1 minus m2 is alpha of some m prime in this formula. And clearly, this is just an application of the map alpha tensor identity to a tensor m prime tensor n. So then I have a composition of the map pi and the map alpha tensor the identity applied to the m prime tensor n. But I already know that the composition of the pi and alpha tensor identity is 0 by the definition of pi. Pi is the canonical surjection on the quotient by the image of this map, alpha times the identity. So this will be 0. I haven't finished maybe the computation, so this is 0. And if this is 0, it means that class of this tensor and class of this tensor are the same, and the definition of G doesn't really depend on the representative. Okay. So the tensor product is exact on the right, but not necessarily on the left. When we discussed the home, there was the idea that the home is exact on the left, but not in general. And then we discussed the nice class of modules, the projective modules, such that home, projective module, and something is always exact. The same idea works for tensor products. So definition, a module is called flat if for any exact sequence, say M, the tensor product M, a module, let's call this module N. A module N is called flat if for any exact sequence M, the tensor product of this exact sequence and M is exact. That's quite a general definition of a flat module. It preserves the exactness by tensoring with this module. Not necessarily, this is any exact sequence, not necessarily finite, but we're going to see in a minute that short exact sequences are enough. So this is part of the following proposition. So proposition, the following are equivalent. So first property, N is flat. The second property is that for any short exact sequence 0, M prime, M double prime 0, the sequence which is obtained by tensoring this sequence with M is exact. So we know in general that there is exactness on the right, but we also have this exactness on the left, additional property for flat modules. So 3, and because we have all automatically have this exactness on the right, so the only kind of non-trivial additional property here in the short exact sequences is the following, that tensor product with M preserves injective mass. Right, so if you start with an injective embedding, take it as a product with N, you still get an injective embedding. And finally, property 4, the last one, tensor product with N preserves injective maps between finite modules. Yeah, so let's discuss proof. In fact, in this proof, there is only one non-trivial implication. How to go from 4 to 3. Well, clearly 1 and 2 are equivalent. Right? Because if you have any exact sequence, exactness of the sequence is equivalent to exactness of the short exact sequences like this. So this thing is exact if and only if you consider exact sequences of the following form. You have some mi, this is mapped to the image of the di, which is surjective by definition, and then you also have the embedding of the image of the di minus 1 plus 1. Right? Exactness of M is exactly exactness of all such short exact sequences, because the kernel of this map, this is projection to the image, is exactly the kernel of the di. So exactness at this term means that the image of the di plus 1 is the kernel of the di. So in particular, you can apply this to the exact sequence obtained with the tensor product and get the result that 1 is equivalent to 2. Now, what else is clear? Well, of course, 2 is equivalent to 3, which is also easy, right? So this is the part 3 is the only non-trivial part of the information in the part 4, because exactness at this term and in this term is automatic, we know this. So the only non-trivial part is exactness at this term is exactly the property 3. So 3 is equivalent to 2. Now, if this preserves injective maps between any modules, so first it preserves injective maps between finite modules, so 3 immediately implies 4. And indeed, the only non-trivial part here is to show that 4 implies 3. So this is what we need to show. Okay, suppose I have a tensor, which is not necessarily simple, so just some tensor, xi, yi, which is in the kernel of the f times the identity on the n. So here, maybe I need to be a little bit more precise what I know in the 4 and 3. I know that I have 0 m prime mapped to the m. Let's call this map f. I know this is injective. And I want to show that I have the following diagram: m prime tensor is n. This is mapped to the m tensor is n. This is f tensor identity on the n. So if I have exactness of this diagram, I want to show that there is exactness at this term of this diagram. So this is where I get this name f. So suppose this is not the case. Suppose I have something in the kernel. Right? So I know it is given to me that this is true for finite modules. I want to show that this is true for not necessarily finite modules. So somehow I want to reduce the general problem to the problem of finite modules. Okay. So what it means that this is in the kernel? Well, I can as well write that sum over I f applied to the xi tensor yi is equal to 0. That's the same thing as saying that this tensor is in the kernel. Now I just consider two submodules. I consider m0 prime inside m prime submodule generated by x1 xn. So I suppose that the sum is I is between 1 and n. So by construction, this m0 prime is a finite module. It is generated by finitely many elements, and in any tensor is a finite sum. So I have only finitely many such axes. So then, of course, this tensor, xi tensor yi, this lives in the submodule M0 prime tensor n. And I also want to define the second finite module M0 inside M. So this is finite submodule generated by the image of this finite submodule M0 prime. So image of any finite submodule is, of any finite module is again a finite module. So this is a finite submodule. So then I can consider map F0, which is just the restriction of the map F to the M0 prime. And by construction, this will be a map from the M0 prime to the M0. Right? So I constructed the finite submodule, and I just take the image of this finite submodule. So I get the map between two finite submodules. And this is already a nice situation, because now I have an injective map between two finite modules. So I can use property 4 in this situation. So if F0 times the identity on the n applied to the same tensor, notice that this tensor still lives in this tensor product. Right? So if F0 times the identity applied to this tensor is 0, well, what it means? It means that I just have F applied to the SI tensor yi is equal to 0, right? So when I want to compute F0 on any such element inside this submodule, I just by definition need to apply map F, because F0 is just a restriction of this submodule. But this is exactly the same condition as before. So if I have a tensor with this condition, it means that I can consider the same tensor in this finite submodule. And because I already know that if I have an injective map, clearly this is injective. So if I have an injective map between two finite modules, then there is no kernel. So it means if this is in the kernel, so SI tensor yi is equal to 0. This is a zero tensor. And this is, if any tensor in the kernel is actually zero kernel, means that this is actually an embedding. So the end of the proof. Okay, so, I'm out of time, several minutes ago, so that's all for today. So next time we will do algebras and then switch to the chain conditions, Artinian modules, Noetherian modules, Artinian rings, Noetherian rings, stuff like that.
Testen, ob sie
Yeah.